Coordinating outlet locations and conduit runs in precast panels requires careful planning and collaboration. When working with precast panels, especially in a gymnasium setting or similar large structure, it's crucial to engage the precast manufacturer early in the design process. The first step involves pre-planning. Provide precise outlet locations and conduit routing in the design drawings. This means detailing where each electrical outlet needs to be located and the exact path the conduit will take within the precast panels. The precast supplier should then design the panel forms to accommodate these electrical requirements. This ensures that the necessary space and provisions are made within the panels during manufacturing. Next is panel fabrication. During panel fabrication, the conduits are embedded within the panels. Outlet boxes and connections are pre-installed in the forms. The coordination during this phase is critical. It's a collaborative effort between the electrical engineer, the precast engineer, and the fabrication team. This team ensures that the conduits are correctly placed and the outlet boxes are securely integrated into the panels. This also includes ensuring that the electrical components are protected during the concrete pouring and curing processes. Moving on to panel assembly. During assembly, the conduits and boxes are connected between adjacent panels. There are several methods to achieve this. Firstly, conduit couplings. Standard or watertight couplings are used to join the conduits between panels. These couplings provide a secure and reliable connection, maintaining the integrity of the electrical system. Secondly, cable connectors. Special connectors allow cables to pass between panels without the need for traditional conduit connections. These connectors are designed to maintain electrical safety and prevent moisture intrusion. Thirdly, junction boxes. Small junction boxes are installed in the joints between panels to facilitate connections. These boxes provide a centralized point for wiring and allow for easy access for future maintenance or modifications. Addressing below-slab conduit runs. Design the conduit runs to terminate at designated points above the slab. This approach simplifies the connections and reduces the need for complex below-slab work. Use a stub-up system. Conduit sections are extended above the slab, allowing for connection after the slab is poured. This method ensures that the conduit ends are easily accessible and protected during the construction process. Coordinate with the concrete contractor to ensure proper placement of conduits and stub-ups. Proper coordination prevents damage to the conduits and ensures that the electrical system integrates seamlessly with the structural components. Connections under slabs are generally avoided in precast construction. It is not typically necessary to connect conduits under slabs in precast construction. If required, precast conduits can be used that extend below the slab during fabrication. These precast conduits allow for connections to be made without disturbing the structural integrity of the slab. The connections can be made using junction boxes or cable connectors after the slab is set. Ensure that the area under the slab is accessible for these connections. This accessibility is crucial for making the necessary connections and for future maintenance. Quality control is essential. Thorough quality control is essential to ensure proper and safe connections. This includes inspecting conduit connections before and after the panels are set into place. Before the panels are set, inspect the conduit runs and connections to ensure they are properly aligned and secured. After the panels are set, verify that the connections remain intact and that there is no damage to the electrical components. Test all electrical systems after installation to verify proper operation. This testing includes checking for proper voltage, amperage, and grounding to ensure the electrical system functions safely and reliably. For more detailed information, consider consulting relevant sections of the National Electrical Code, such as Article 300.10 regarding mechanical continuity of raceways and cables, and Article 314 regarding junction boxes, pull boxes, and handle enclosures. These sections provide specific requirements for the installation and protection of electrical raceways and boxes. When installing electrical systems in precast panels, it is important to follow best practices for grounding and bonding to ensure electrical safety. Grounding and bonding create a low impedance path for fault current, which helps to protect people and equipment from electrical shock and damage. The National Electrical Code Section 250.4 provides the general requirements for grounding and bonding, stating that electrical systems must be grounded in a manner that limits the voltage imposed by lightning, line surges, or unintentional contact with high voltage lines, and that stabilizes the voltage to F during normal operation. The grounding electrode system typically includes a grounding electrode conductor connected to a grounding electrode, such as a ground rod, metal water pipe, or concrete encased electrode. The size of the grounding electrode conductor is determined by NEC Table 250.66, based on the size of the service entrance conductors. Bonding ensures electrical continuity and conductivity by connecting all metal parts that are likely to become energized to the grounding system. The NEC Section 250.92 requires bonding of service equipment, including metal enclosures, raceways, and cable armor. Bonding jumpers are used to connect these metal parts to the grounding bus or terminal. For interior metal water piping systems, NEC Section 250.104 requires bonding to the grounding electrode system. The bonding conductor must be sized according to NEC Table 250.102, based on the size of the service entrance conductors. In precast concrete construction, special attention must be given to maintaining effective grounding and bonding. When conduits are embedded in the concrete, they must be securely connected to the grounding system. This can be achieved by using grounding bushings or connectors that are listed for direct burial in concrete. If junction boxes are used, they must also be bonded to the grounding system. Metal junction boxes must be bonded using grounding screws or clips, while non-metallic junction boxes must be equipped with grounding terminals for connecting the grounding conductors. When connecting conduits between precast panels, it is important to maintain electrical continuity. This can be achieved by using listed conduit couplings that are designed to provide a reliable electrical connection. The couplings must be tightened properly to ensure a low impedance path for fault current. If flexible metal conduit is used, it must be bonded at both ends to the grounding system. The bonding jumpers must be sized according to NEC Table 250.102, based on the size of the circuit conductors. In addition to grounding and bonding, surge protection is an important consideration for electrical systems in precast concrete buildings. Surge protective devices, or SPDs, are used to protect sensitive electronic equipment from voltage transients caused by lightning, switching surges, or other electrical disturbances. The NEC Section 230.67 requires surge protection for dwelling units, and it is also recommended for commercial and industrial buildings. SPD are typically installed at the service entrance and at branch panel boards to provide comprehensive surge protection. They work by diverting excess voltage to the grounding system, preventing it from reaching sensitive equipment. When selecting SPD, it is important to consider the voltage rating, surge current capacity, and protection mode. The voltage rating should be appropriate for the system voltage, and the surge current capacity should be sufficient to handle the expected surge currents. The protection mode refers to the way the SPD protects against surges such as line to ground, line to line, and line to neutral protection. Another important aspect of electrical design in precast concrete buildings is lighting. Proper lighting design is essential for providing a safe and productive environment for occupants. The Illuminating Engineering Society, or WISE, provides guidelines for lighting levels in various spaces, such as offices, classrooms, and factories. The lighting design should take into account the task being performed, the age of the occupants, and the reflectance of the surfaces in the space. Energy-efficient lighting systems can help to reduce energy consumption and lower operating costs. LED lighting is becoming increasingly popular due to its high efficiency, long lifespan, and excellent color rendering. LED fixtures are available in a wide range of styles and wattages, making them suitable for various applications. Lighting controls can also help to reduce energy consumption by automatically dimming or turning off lights when they are not needed. Occupancy sensors can detect when a space is occupied and turn on the lights accordingly, while daylight harvesting systems can adjust the lighting levels based on the amount of natural light available. In addition to general lighting, emergency lighting is an important safety feature in precast concrete buildings. Emergency lighting provides illumination in the event of a power outage, allowing occupants to safely evacuate the building. The NEC Section 700.12 requires emergency lighting to be provided in essential areas such as exit stairways, corridors, and assembly areas. Emergency lighting systems typically consist of battery-powered lighting fixtures or generators that automatically activate when the normal power supply is interrupted. The emergency lighting must be designed to provide adequate illumination for at least 90 minutes. The design of the electrical system in a precast concrete building must also consider the requirements for fire alarm and life safety systems. Fire alarm systems are designed to detect fires and alert occupants to evacuate the building. The NEC Section 760.41 covers the installation of fire alarm systems, requiring them to be installed in a manner that prevents false alarms and ensures reliable operation. Fire alarm systems typically include smoke detectors, heat detectors, manual pull stations, and audible and visual notification devices. The fire alarm control panel monitors the status of the detectors and initiates the alarm signal when a fire is detected. Life safety systems include emergency communication systems, smoke control systems, and elevator recall systems. Emergency communication systems provide a means for communicating with occupants during an emergency, while smoke control systems help to remove smoke from the building to improve visibility and reduce the risk of smoke inhalation. Elevator recall systems automatically return elevators to the ground floor in the event of a fire, preventing occupants from being trapped in the elevator. The electrical design for these systems must comply with the requirements of the NEC and other applicable codes and standards. The selection of electrical equipment for precast concrete buildings must also take into account the environmental conditions. In areas that are exposed to moisture, corrosive substances, or extreme temperatures, special electrical equipment must be used to prevent damage and ensure reliable operation. For example, in wet locations, such as bathrooms or kitchens, ground fault circuit interrupters, or GFCIs, are required to protect against electrical shock. GFCIs detect small amounts of current leakage and quickly interrupt the circuit, preventing a person from being electrocuted. In corrosive environments, such as chemical plants or wastewater treatment facilities, corrosion-resistant electrical equipment must be used. This equipment is typically made of stainless steel, fiberglass, or other materials that are resistant to corrosion. In areas with extreme temperatures, such as freezers or ovens, electrical equipment must be rated for the temperature range. High-temperature wiring, insulation, and enclosures must be used to prevent damage to the equipment. The installation of electrical equipment in precast concrete buildings must be performed by qualified and licensed electricians. The electricians must be familiar with the NEC and other applicable codes and standards and must follow the manufacturer's instructions for installing the equipment. The electrical work must be inspected by a qualified electrical inspector to ensure that it complies with the codes and standards. The electrical inspector will check the grounding and bonding, wiring methods, overcurrent protection, and other aspects of the electrical system to ensure that it is safe and reliable. Regular maintenance and testing of the electrical system is essential for ensuring its continued safe and reliable operation. The electrical system should be inspected annually by a qualified electrician to identify any potential problems. The inspection should include checking the grounding and bonding, wiring connections, overcurrent protection, and other components of the electrical system. The electrician should also perform insulation resistance testing to identify any deterioration of the wiring insulation. The results of the inspection should be documented, and any necessary repairs or replacements should be performed promptly. In addition to annual inspections, periodic testing of certain electrical equipment is required by the NEC. For example, GFCIs must be tested monthly to ensure that they are functioning properly. Emergency lighting systems must be tested monthly to ensure that they are providing adequate illumination. Fire alarm systems must be tested annually to ensure that they are detecting fires and alerting occupants to evacuate the building. The testing should be performed by qualified personnel and the results should be documented. In summary, coordinating outlet locations and conduit runs in precast panels requires careful planning, collaboration, and attention to detail. By following the best practices for pre-planning, panel fabrication, assembly, below-slab conduit runs, and quality control, you can ensure a seamless electrical integration that meets the needs of your client and complies with all applicable codes and standards. Remember that grounding, bonding, surge protection, lighting, fire alarm systems, and environmental considerations are all important aspects of electrical design in precast concrete buildings. By addressing these aspects, you can create a safe, reliable, and energy-efficient electrical system that will serve the building and its occupants for years to come.